Hello and welcome to section 1.6 continued. So we've moved to the second type of equation. We talked about fractions, how fractions can come along in equations, and we got to clear our fractions and be careful that the solutions work back in the problem. So the second thing you'll find in your book, and if you're following along, I am doing example 3 on page 138, and we're going to talk about solving work rate problems. So these are work applications. The base formula we need is that work is rate times time. It's almost like distance. You might say that sounds familiar because distance is also rate times time. So distance, like how far you get, is sort of like work, how much work you get done, how much distance you get. So they're very related. You know, if it takes me 3 hours to complete a job, so my rate would be 1/3 of a job per hour, and I work for 2 hours, my rate times time, I would have 2/3 of my job done, and that's sort of where it's coming from. So let me show you what I mean here. Again, work is your rate, of course, how fast you work is going to affect it, and how long you work. Those are the two factors that affect how much work you get done, actually multiplied together. So the way we express our rate, though, is, I won't say like I work at 60 miles an hour. I guess maybe there's some way to think through it like that, but normally not. They'll just say Cindy takes 3 hours to mow her lawn or clean her house or whatever it is. There'll be a certain amount of time it takes me to get that job completed. So for example, so your rate would be 1 over however long it takes you to complete the job. So for example, if I'm mowing the yard, cleaning the house, my work that I'm doing takes me 3 hours, it would be 1 over 3 job per hour. I'd have 1/3 of the job done, basically. And then if I work 2 hours, I'm going to have 2/3 of the job done. And if I work all 3 hours, I will have completed my job if I know my rate is 3 hours. So that's kind of how those flow. This is the base idea, rate times time. All right, so here's what always happens, though. What we do to you in this advanced algebra is we have two people working together instead of just one thing. We compound it with having 2 people working together or 3 people working together. So we always suggest a chart or a picture sort of helps you organize that, and that's why you'll see these charts a lot of times. So keep in mind that the idea is work equals rate times time. So say you've got these 2 people, person 1, person 2, and it takes me 3 hours to, let's go with clean my house, 3 hours to clean my house, and then a friend is helping me, and they work a little slower, of course, right? I'll say that. It takes them 4 hours to clean the house if they were working alone. So how long will it take them if we work together? Well, you know, that's a big help to me, even if it is a little slower. It should be something, maybe 2 hours, maybe it's an hour and a half. I don't know what you think, but it's going to make the job done a lot quicker. But again, we don't write it as 3. I write it as 1/3. That's my rate. That's my friend's rate. 1/4. 1 over your individual time makes your rate. So we don't know how long we're going to have to work together to get the job done. So that's going to be my unknown in this problem. I'm going to say, how long are we going to work together and get this house clean? So the rate times time tells me how much work I get done. Multiplied together, that's my work at any time, point in time, 1 hour, 2 hour, whatever. And the other person is 1/4 T, is that work. Now this might be a little different than the distance problem, because what we always do with these is we add them. We want this work plus this work to equal 1 job completed. Well, normally we want 1 job completed. I suppose we could say how long till we're half done and so on, but typically the ones you'll see too in your book, we set them equal to 1. When they're working together, it's an addition. If we were working against each other, and there are scenarios where that could be true, if I was working, the other person was undoing behind me the work, we would subtract. And we see that, there's an example we'll do in a little bit where there's an inlet pipe filling up a pool, but there's a leak that's emptying out the pool, so we'll talk about how that would subtract. But you know, normally if 2 people working together, this typical problem we add equal to 1. All right, we do need to clear the fraction. Always clear fractions when they're involved. So I would times by 12. 12 times 1/3 is 4. 12 times 1/4 distributed is 3. And 12 times 1 is 12. So that gives us 7t equals 12. Divide both sides by 7. T is 12 over 7. So that's a little less than 2 hours, right? 12/7 would be 1 full hour, and then 5/7, which we could convert that to minutes, but we won't make you do that. You know, that will not be required. So 1 5/7 hours is what it would take if me and my friend were working together to clean that house. That seems reasonable. Now, let me tell you a little story about this. This always makes me think of this. When our kids were little, and I can't remember which kid, but we were going to an academic meet at their elementary school, and I don't know if you've ever been to one of those, but they have this quick recall, and they answer questions in like 5 seconds. Really hard math problems sometimes, and me being a math teacher, I'm always amazed by that. And I remember there was one of these particular problems on the quick recall match, and I know it takes this type of algebra to do it, and that cannot be done in 5 seconds. No way. So I was intrigued by that. Well, anyway, maybe you've already seen this or figured this out. At 12 and 7, there's a shortcut to get to this, and they knew that, and the quick recall coach, I guess, had told them how to do this. But they were missing the whole point of why it worked, you know, but they did know the trick, which was if you have an individual time of 3 hours and an individual time of 4 hours, 12 and 7, you might notice, is 3 times 4 over 3 plus 4. So that can be quickly calculated. You can jump right down there. If it is of this type exactly, if you know the 2 individual times, again, a 3 and a 4 hour worker, multiplied is 12 over added is 7, will work every time. So say 4 and 5. If you knew someone takes 4 hours to mow the lawn and their buddy takes 5 hours to mow the lawn, when they work together, it'll be 4 times 5, 20, over 4 plus 5, 9. 29. It's a little over 2 hours for those 2 people to work together. So just thought I would let you know that. But this is the backstory. And if it was anything other than this method, if they had any other mix-up with it where you didn't know the individual times, you couldn't use that trick. So, but oftentimes you do know the 2 individual times, and this is just a great, it's a great thing to be aware of. All right, now let me do the one that's in your book, example 3. This work problem, we couldn't use our trick on, so we would need to know the base way to do this. It's one, and again, you can follow along, 138, but I'll read this to you. It says, one printer can do a job twice as fast as another, but working together, both printers can do the job in 2 hours. How long will it take each printer working alone? So we don't know the alone time. We don't know the individuals, what I would call, I said it takes me 3 hours to clean the house. We don't know that individual part. We know the together time. So this one's mixed it up on us a little bit in what we know. But the formula is still the same idea. Work equals rate times time. And we got 2 things going on all of these, so that'll help us chart it. So what we do know is the together time in the reading, it says it takes them 2 hours to do the job working together. So we know the time they're going to work is known there, 2 hours. So our variable is going to show up in the rate. We don't know the rate. What we know is one of the printers is twice as fast as the other one. So if we let this rate be the base unknown rate, and it doesn't matter which one you call which, however you want to design it, the base unknown, we don't know how long that printer works alone. The other one takes double that, twice as long. So if this one's 2 hours, this one's 4 hours, 3 hours, 6 hours, and so on. It's twice as slow. Takes twice as long. But same idea, we multiply rate times time, and let's talk about that being over 1. So 1 over x, 2 over 1, you can multiply the tops and the bottoms and have 2 over x when you multiply. So when you multiply that on top, that's over 1, it's 2 over 2x. The 2's cancel and you just got 1 over x. And just like on the other one, once you've represented your 2 workers, you add them and we set them equal to 1 completed job. Again, those fractions on this, so we want to clear the fractions. The LCD is just the x variable times that to each side. Distributing the x is canceled there, leaving a 2. Distributing here, the x is also canceled, leaving a 1. And the x times 1 is x. 1 plus 2, simply adding on this left side, is 3. So that tells you that the faster printer took 3 hours to complete the job. So their rate is 1/3 of a job per hour. And this one is twice as long, 1 over 2 times 3, or 1/6 on that. All right, so that's your work type of problems. All right, the next topic that we go into, and like I said, this section is all about just various types of other equations that show up. So our next type is radicals. So if you want to look on page 140, and the green box will tell you, actually there's 2 green boxes. It tells you that if you have an equation, P equals Q, you can take each side to a power and it's still equivalent. Like if we take it to P to the N, meaning N being any power, you can square both sides, cube both sides, take it to fraction powers, whatever you do, you can do it to both sides. But sometimes when you do that, you get extraneous solutions. Sometimes some of the answers don't work in the original, but you'll always find all the solutions that way, but you'll just need to check them because you may get some extra ones thrown in there, especially because of their sign or something. For example, if we had the equation x equals -2, that's an equation. We're allowed to square both sides. That's keeping the balance. So when we square it, we get x squared, and say we're squaring that side, so it actually becomes +4. Well, when you plug that back in, x squared equals 4. That actually changes the value. I guess I should have gone the other way. Anyway, I'm going to scrap that one, but just say that sometimes you compromise the sign by squaring both sides to an equation that was negative, but because of the squaring of each side, you've compromised the sign. So, and they illustrate that you can have different solution sets on page 140. All right, but I'm going to go ahead and start my example 4. And show you how we'll use it in practice and how that we do sometimes get these extraneous solutions. So here's an equation that contains a radical. And our goal is always to have x equals an answer. No radicals in it, just plain old 1x out of the radical and all. So we need to get rid of the radical basically and have regular x. So what we want to do is get the radical isolated on one side and then square each side so we can square the square root, and that will get rid of that. But like I said, sometimes it compromises the sign. So I'm going to take this radical term, isolate it by taking it to the right side. Now notice when I move a radical term, the stuff under it, the radicand, does not change anything about it. It's the same stuff under the radical, but the outside sign, the coefficient -1, when moved across the line becomes +1. So that is important to note. Don't change your radical stuff, move it across, but the coefficient does change its sign, because you're adding this to both sides. So it cancels off of this side. Anyway, now that the radical is isolated, we can square this side, and the radical and the squaring would cancel each other out and release the radicand stuff, but you have to do the same thing to both sides. Okay, so now we get a quadratic equation, which is something we have done. We've dealt with these. We know to solve a quadratic, we bring everything to one side equal to 0, and then we either factor it or use our quadratic formula to solve it from there. So it does factor into x plus 5 and x minus 3. Setting each part equal to 0 by the zero factor property, we get 2 potential solutions, but this is where we'll see they don't always work out, and they illustrate that in your book in case that we run out of time before you see me finish it. When we plug -5 back into the original, it doesn't actually work. Solve it. Now, even though all the algebra looked good, but this is where I'm saying where we squared maybe a negative somewhere along the line, we may have compromised the solution. But what we do know, this is the method to get to all the potential solutions. They just must be checked to verify which ones work. So checking this out, let's see, that's 15 plus 10 actually, which is 25. So we got -5, subtract, that would be 5. And that side is actually -10. So that is not true when you check it back in. So that one's thrown out. We then start over, check the 3, and it actually does work out. So that is the one and only solution.